Hello and welcome to another video. In this video, we'll implement the original Generative Adversarial Network or GANs research paper that came out in 2014. So first of all, let me just quickly state what GANs are actually used for. So as the name itself suggests, they are generative networks, right? So they are used to generate data itself. So if you are a deep learning practitioner, so you might have already seen that neural networks are used to classify and sometimes used for regression. So they're used to discriminate or produce some result using some data, but they don't actually produce some data. So for example, here in front of you, you can see these images. These are not real persons. These are images produced by GANs trained on very special data, right? So they produce realistic looking images like these. And this is a Medium article. It's a really cool article about some cool applications of GANs, so you can go through this. So let me quickly just show you a lot of the results that have been achieved using GANs, and then we'll start to read the research paper, and then we'll actually implement the research paper. So yeah, GANs are nowadays being used to auto-generate and colorize the anime characters. As you can see, all of these characters are produced by GANs. These are not real characters, right? And here is some network architecture detail that I'm going to skip right now. And then yeah, post generation of and then one more interesting, the cycle GAN is really interesting because this type of GANs are used to actually transfer style from different types of images. So for example, you see this normal photograph right here, so we can transfer Monet, Van Gogh or different painter style to this photo. So as you can see, the results are right here. And also you're converting zebras to horses and horse to zebra, and that's just so realistic looking. So there are a lot of other examples. So as you can see, you just read this article, it's really nice. And yeah, this is also really cool application. I find this really cool because this is super resolution. So it takes input a really distorted an image with very low resolution, and then it can transform it to high resolution image. So this is the original image, and these two are the results produced by GAN. So these are very close, and yeah, as you can see right here. So yeah, there are a lot of other results, groundbreaking results. So you can achieve all of these things using GANs. So now let's quickly proceed to the research paper. So here it is, and let me just hide this pane, or let me just leave it right there. Okay, so as you already know, GAN, Generative Adversarial Networks, was invented by Ian Goodfellow. He is the main author of the paper. So let me just quickly read out the important parts that I'm going to cover in the research paper. So this abstract, the first paragraph of the abstract. So he says that we propose a new framework for estimating generative adversarial models using adversarial processes. Okay, so sorry for the disturbance. So yeah, a generative model G that captures data distribution, a discriminative model D that estimates the probability that data came from the training data rather than G. So it basically means that we are trying to train two models that are going to fight each other. So a generative model, the name itself suggests that it will generate some sort of data, and the discriminative model will try to guess that if that data is the original data or it's been generated. So we'll try to train both of them to fight each other, and in this way they both will get better. Generative network will get better at generating data, and discriminative model will get better at discriminating the data. Okay, so yeah, so it basically means that the last line that I've highlighted, this framework corresponds to a minimax 2-player game. So yeah, that's it. And then you can read the introduction, but it basically says that there are a lot of things that deep learning can do well, but generative models was not a strong point for deep learning models because there were a lot of complications with maximum likelihood estimation and all of those things. So but this adversarial networks, these take a very different route to just bypass all of that, and they propose a generative model. So I'll just quickly read that out. Deep generative models have had less of an impact due to difficulty of approximating many intractable probabilistic computations that arise in maximum likelihood estimation, as I've already told. And so due to that, deep learning models were not used for generative purposes. So here it says that we propose new generative model new generative model estimation procedure that sidestep these difficulties. And here's another example of another way you can think about generative adversarial models, and it's a really nice example. So as he states, the generative model can be thought of as an analogous to a team of counterfeits trying to produce fake currency and use it without detection, while the discriminative model is analogous to the police trying to detect the counterfeit currency. Competition in this game drives both teams to improve their methods until the counterfeits are indistinguishable from the genuine articles. So yeah, that's what's happening. Both of them are improving their game. So that's exactly what's happening here. So yeah, it goes into more detail about how these networks work, and then here in related work you'll find out about the different architectures that were used before this to generate images. So Boltzmann machines, I'm not going to cover all that, and here also not talked about all these things in the paper. It's just mentioned the related work which can be read if you want to. Now let's quickly move on to the adversarial nets, actually how to train them. So there is a lot of math here. So basically adversarial networks, well, discriminator represents the probability that X came from other data rather than the probability distribution of the original data set, right? So we train D to maximize the probability of assigning the correct label to training examples and samples from G. And so while we're training that, we simultaneously train G to minimize log 1 minus discriminator of generative of the some noise data. So I'll just go into detail about this loss function. So yeah, finally the loss function. In other words, D and G play the following two-player minimax game with value function. Value function can be seen as a loss function here. So it's basically a cross entropy loss which can take only two values, zeros and one. So it's basically a binary cross entropy function. So for training the discriminator, it's basically straightforward function that is a cross entropy loss. So let me just quickly open this loss function. So here is the cross entropy loss, or binary cross entropy loss, because here y can take only two values, zeros and ones, right? So this is a binary cross entropy loss. Okay. So for the discriminator, let me just write the discriminator. We use the original function, right? So by that I mean that we don't need to modify this function at all. If the discriminator guesses that the output is correct, that is it has come from input data, so and the output it is correct, then we won't add anything to it, because this term will become 0, 1 minus 1 will become 0, so we won't add anything here. And if it suggests something wrong, then we'll add this term, right? If it suggests it's 1 but it's 0, so all that, those things, normal cross entropy loss. Let me just erase this. But what happens is, as you can see in the discriminator, he writes that we need to minimize log 1 minus d. So this part, basically this part, we need to minimize this. So minimizing this term is same as maximizing this term, okay? And maximizing this term is same as minimizing the negative of this term. So what we'll do is we'll try to calculate this term, the whole negative term for discriminator, for generator, and then we'll try to minimize this. So let me just quickly once again go through this. So it's really confusing. We try to minimize this function, right? 1 minus whatever the prediction is, log of that, right? So it basically means he's asking us to minimize this, but it's quite easy to minimize or to maximize this. So instead of minimizing this part, we can also do the same thing, that is maximizing this. If we try to maximize this, it will automatically get minimized, right? So we try to maximize this, but gradient descent can minimize a function easily. So what we'll do is we just add a negative sign here, which is the normal cross entropy loss function, and this negative sign will help us minimize this function. So let me just get rid of all these things, and let's see what exactly we're going to do. So what we'll do is, first of all, when we train this function or this network, we have a function called binary cross entropy loss. So it will take your predictions and the real outputs, the real labels, right? So whenever we'll try to calculate loss function for the generator, what we'll do is we'll pass in the outputs of the discriminator and the labels. The labels will be all set to ones. because we try to calculate how easily our generator can fool the discriminator here. So the label should be 0, but we'll pass all ones and try to see how this loss function performs, how this loss function decreases over time or increases over time. So that this is the basic concept behind that. So we try to fool the discriminator and pass all 1 labels instead of all zeros. Zeros means that it is not the data, it's not come from the data distribution, it has been generated, but we'll pass 1 to see if we can fool the discriminator. So that's it. It seems really complicated, this whole cross entropy loss function. So what you can do is just go through this function and try to find the output. Try to simplify this function for 2 cases. If y of I, which is the output, is equal to 1 and y of output is equal to 0. So if y is 1, this entire term will just vanish, right? And if y is 0, this term will vanish. So that's what's happening. If we pass in 1 with the discriminator or the data generated by the generator, so if we pass 1, then automatically this term will get cancelled. So we are trying to, for generator, we are just trying to minimize this function, that is minus of yi log p of yi. Now which basically means that if you try to minimize this function, we will basically maximize. If you remove minus sign, we are maximizing this. So we are maximizing this, and that's what he's asking. Okay, so finally let me just move on to the code. Okay, so here is the code, and you can find the code in the link in description. So I've imported all of these libraries needed here. So I'm going to be implementing this in Pytorch. So first of all, we'll make a directory for the output. Now the image shape. So let's just quickly go through the research paper, the last parts of the research paper. So it basically now tries to give it a theoretical treatment to the concept, and it will try to prove how these networks or how these networks can actually converge. So theoretical results. First of all, is the algorithm. So what it's doing is sample mini batch. First step is to sample noise examples, mini batches of noise, and noise will be treated as the we'll just pass in the noise to the generator, and it will convert this noise to an image. And then we'll sample examples of the real training distribution, and then first we'll update the discriminator by using this basic cross entropy loss, and then we'll sample the mini batch to produce the image, and then update the generator using this, as we have already covered this function basically. And then we'll just do that until we reach the desired results. That's it. Now here it will prove that global optimality of this results is achievable and all of that. So we'll just quickly skip that because it requires a lot of advanced mathematics, 2 or 3 theorems, and then different experiments, right? So experiments with MNIST is, as you can see here, it produces these kinds of results. So these digits are produced by the network itself. These are not present in a dataset. The exact digits are not present in a dataset. So you can train it on various kinds of datasets, and it will produce really great results. And at that time, in 2014, these were really groundbreaking results. So that's why GANs are being explored in the research a lot. So yeah, that is it. And then conclusion and all of that. So if you want to go through all the advanced mathematics, you can just go if you can. So yeah, but you don't need to, because now we have understood the concept and we'll try to implement the research paper. Okay, so we are trying to use MNIST and trying to recreate this result using MNIST. So MNIST dataset has 28 by 28 images. So I have already described image shape here. Now generator class is a class that generates the fake images by taking input some random noise. So the random noise size will be 100 pixels. So yeah, we have a linear fully connected layers, first FC1, FC2, FC3. So it will just go from 128 and then to 512 and then to 1024, and then finally we'll just from 124 to 28 by 28. And I've made this batch now, so I've normalized the images, and I'm using leaky ReLU activation function, not the ReLU itself, because it's image data and we need some sort of threshold. We cannot just put all the values to 0. So that's why I'm using leaky ReLU, and most of the GAN research paper use leaky ReLU. There are a lot of things, complications with GANs. These are being explored, right? If you use ReLU, the results are really distorted. So I'm using leaky ReLU. It's just activation and instance normalization, batch normalization here. And then finally, it's just straightforward. Finally, we are using the NH activation function because most of the implementations do that. You can also use ReLU. There's no point in not using that, but NH results are a bit more visually pleasing. So yeah, there's that. And then finally, before returning the image, we just change the image to this size, 1 by 28 by 28, so that it's easier to just view that. So this was our generator function. It will generate images. Now another function, another network that will discriminate, that is guess whether the image is from the original dataset or it is being produced by the generator, is this discriminator. So it basically takes in the input 28 by 28, and then fully connected layers are there, and then finally it will produce a sigmoid output. So again, I'm using leaky ReLU function, so you can do that. It will return a sigmoid activation. Now we are going to be using BCE loss function that I've already covered here. What it does, it basically a cross entropy loss function with only 2 values, that's binary. Now we'll create generator and discriminator instances right here. Now we are trying to create our own dataset, download the dataset. So if you don't exactly know how to do this in Pytorch, just follow my Pytorch series. It covers all of these things. So I have the link in description if you want. So here it says to download the MNIST training set and then convert that to tensor and then normalize it. The batch size is set to 64 and we want to shuffle that. So all of these things are done. So we have the data set here. Now this part checks if CUDA is available. If you can use CUDA, then it will just transfer all the generator, discriminator and loss function to CUDA, that is a GPU. And then we'll use optimizer optimizer for both generator and discriminator. So we are going to be using Adam. The original paper used momentum. I have used both of those, and Adam produces better results. And then we are gonna optimize the parameters of the generator and discriminator. Again, I'm gonna be using loss function. Learning rate is set to 0.0002. You can experiment with that. I have experimented a bit, and this was the best I could do. Now betas are usually set to 0.9 and 0.999, but here I've set it to 0.4 because on experimentation I found out that reducing the value of beta 1 produced better result always. So you can again experiment with this value, it's always possible. And then tensor, we're just saying that if we are going to need to create few tensors here. So if CUDA is available, we'll use CUDA float tensor. If not, then we'll use Torch float tensor. Now this is the training part. So I'm gonna run 20 epochs. You can run more if you want. The quality will increase, quality of the outputs of course. And then I'm gonna enumerate the dataset and extract each mini batches here. We don't need the labels because we are not trying to train the classifier, so we just need the images. So here we're just discarding the labels. So these are the ground truths, which means let's say the batch size was 64 right here, as you can see. So if there are 64 is the batch size. So if we'll process in the loss function, if we'll process the real images, this val function, that means it stands for valid, so we'll pass the invalid, which is a tensor of all ones. If it is a fake, then we'll pass in the tensor of all zeros. So it will just act as this yi here. It is 1 if the result is coming from the original dataset. It is 0 if the results coming from the generated dataset. So it acts as just the y, the target label. So yeah, it will be clear as we just move forward. So real images. So real images means the image in the dataset. So I'll just pass it to CUDA, and then optimizer.0grad to just flush the buffer if there is some gradient stored. So you should do that every time. And then these are the generated input. So which means the input to the generator, gen input. Now we'll create a tensor of random noise of size 100, and then we'll pass that to generator, and the generator will produce some outputs which will be stored in generated images. So we have fake images, the real images and the generated images. Now the generator's loss function. So as we have already said, the loss function here to BCE, which is binary cross entropy loss. We'll pass in the discriminator, the result of discriminator on generated images, and val, which means we are passing 1, and it should be zeros, but we are passing 1 to just see if generator has been able to fool the discriminator, or to calculate the level to which the generator can fool the discriminator. There's that. And then we finally run the backpropagation algorithm, and then we'll run the optimizers step. So here we have completed training one iteration of generative network. Now let's move to the discriminator. So let's set to gradient to zeros. Let's flush the buffer, and then real loss, which means the loss function of real images. So how good it does on classifying real images. So we'll pass the discriminator, real images, and these are valid. So yeah, valid images. Of fake images, again we'll pass the loss function and discriminator on fake images, and then we'll just calculate the average of those two to calculate the discriminator loss here, and then we'll run backward and step, which means the backpropagation algorithm. Okay, so one thing you might notice is that I have averaged these loss. There are many implementations that do this, and there are many that just separately measure the real and fake loss. You can do that too for a detailed measure of performance, but here printing, I had to print all of these things together, so it looked better to print that and it looked really less complicated, so I use this method. And finally we are printing epoch number, batch number, discriminator loss, generative loss, and the dataset, all of that. And for every 400th iteration, that is epoch into length of dataset plus I, that is the enumeration, will just display the output. So you can find the link in description. So as you can see, I have already executed while I was just recording the video. I have set this to execution mode, and then it has executed. So as you can see, the loss function varies a lot, especially the generative loss, not the discriminator loss. Discriminator is decreasing rapidly and regularly, but there's a lot of variation in generative loss. So it does not mean anything except that, you know, our discriminator is trained better than our generator. So discriminator's network was much stronger. So if you just vary this network a bit, you know, try to reduce the number of layers and try to reduce the accuracy of discriminator, maybe generative loss will decrease and discriminator loss will stabilize at some point. So it means that. And again, loss functions in GANs are, you know, really unpredictable sometimes. So let's just look at the output. So we have this file that we have executed here. Our data has been downloaded by Pytorch, and then this is the output folder. So as you can see, it starts off with, you know, random noise, and it gets better and better. Let me just make this bigger. Yeah. So it gets better and better at, okay. So there's less noise in the image as we proceed further. So if you train for longer iterations, it might do even better, but this is great to demonstrate the results. So we have officially, or let's just say successfully, you know, yeah, reproduce the result here. So you can just try to run this test on various other data sets. So this was really a groundbreaking paper because it, you know, generation was thought to be really difficult. We used really complex mathematical process, but Ian Goodfellow proposed this kind of network, and it ever since that this research paper came out, there has been a lot of ongoing research in that field. And as I've already introduced you to this article, just go ahead and see how many possibilities, how many ways to, you know, just manipulate data using GANs are there. So it's amazing. And I'll also cover more on GANs. So in the next video, we'll try to implement deep convolution GANs. So it basically improves further on GANs, and it produces even more visually appealing results. And after that, we'll see what we can do. So thanks for watching, and stay tuned for the next one. Goodbye.